Yes. Hello, everyone. So, today we're going to discuss a very, very, very important question because this question is based on EMI, and this can be considered as a master question. Because what is a master question? It's a question which will be discussing different concepts, or by understanding that question we can say we have understood multiple questions, sorry, multiple concepts. So this is that kind of a question where by dealing with this question I'm pretty sure that you'll be able to understand motional EMF, Faraday's equation, and vector form of motional EMF. All these things will try to accommodate into this one question. So this video might be a little long, but at the same time, it will be very informative. With this one video, you'll be able to understand, we can say, 60 to 70 percentage of the entire chapter of EMI's finding EMF concept. Okay, so let's try to understand the question. It says that a regular loop of dimension L and W moves with a constant velocity V away from an infinitely long straight wire carrying a current I in the plane of the loop as shown in the figure. So you can see it on the figure. Let the total resistance of the loop be capital R. What is the current in the loop at the instant the near side is a distance h from the wire? So at that particular instant, what they're showing in the figure, at this instant, what is the current they're asking? And also at the end, the important part, can you derive the same result using the given equation? That given equation is actually the vector form of the motional EMF. Okay. So anyway, so first of all, let us draw the diagram, and let me draw the diagram here. So this is, let us say, the current carrying wire. As per the question, they are having the current going in this direction as I, and they are having a loop with resistance like this. Okay, and this loop is having a velocity in this direction of V. The length of this side, they are calling it as L, and this side length they are calling it as W, and this resistance value they're calling it as R. The current is I. These are the given data. So first of all, they want what is the current in the loop when the distance from here, this distance becomes h. That's the question. So at that time, how much it is? Okay, so we can find this in three ways. Okay, so let me start with this. Let us find first of all the EMF induced the loop by using the concept of Faraday's law. According to Faraday's law, rate of change of flux is going to give me the EMF. So let us first talk about this in terms of flux. So right now, at this moment, at which moment? That's a question. Which moment means, let us say this distance at this moment is y. It's not h. They want you to find at h, right? Currently, I'm assuming it has some y, let us say. So at this current moment, you're interested in finding the flux that is passing through it. So to find the flux, again, like a previous video that I have uploaded, you can check that. Flux because of a wire, you have to find out by integration. So here also I'm going to take a strip. Okay, let us say that the strip here that I have taken is at a distance of x from the wire, and the thickness of the strip is very small, dx. So I can assume that throughout the thickness of the strip the magnetic field will be remaining constant, because magnetic field due to wire is given as a mu naught I by 2 pi r, where r is the distance from the wire. So if that r is not changing much, then the magnetic field also will not be changing much. So yes, I'm talking about a distance x, and then from the x a small distance dx, so it is not changing much. So I can now write the flux in this region as a small flux d phi is equal to b into a into cos is, this is the angle between the area vector and magnetic field. If you look at the wire, if I try to hold the wire with my right hand, by using right hand thumb rule, I find that the magnetic field is going inwards. So if magnetic field is going inwards, then magnetic field direction into the board, area vector direction always perpendicular to the area. So that also I can assume into the board. The angle between them will become 0. So now it will becoming mu naught I by 2 pi r. R is a distance, that's nothing but x, into a. What's the area of the strip? The area of strip is, it's a rectangle. Length of the strip is L. The thickness is dx. So it will be L into dx. This is the flux for that small section at this moment. Which moment? When the distance is y. Will the y remain constant for different time? No, right? Because see, this coil is having a velocity. The coil is keep on moving in that direction, and because of the motion of the coil in that direction, the y will keep on increasing. So I am just finding it for a particular moment. So for me, the time is right now constant. Okay, because I am only discussing at a particular moment. At this moment, when I am finding the flux, I found only flux for one strip. I want the total flux. It will be nothing but integration of d phi. So integration of this value mu naught I by 2 pi x L dx. What is a variable here? That's very important. The variable is actually my x. Okay, so from where to where I have to integrate? I have to start my integration from y to y plus w. So limits is y to y plus w. So when I do that integration, I'll be getting it as mu naught I L divided by 2 pi. Integration of 1 by x will become natural log of x. But when you substitute the limit, it will become y plus w divided by y. This will be the total flux linked with that loop at this current moment. Now I am not interested in the flux. I am interested in rate of change of flux. So what I should do is, because I want EMF, right? So EMF is equals to d phi by dt. See, I'm only going for magnitude. Actually, there is a negative sign here, but you know that negative sign only represents that the induced EMF always opposes the cause, Lenz's law. So I'm only going with the magnitude here. So that magnitude will come out to be E is equals to d phi by dt. If I differentiate this with respect to time, you can say that mu naught I L 2 pi. They are anyway permanent constants, so you can take it out. Mu naught I L divided by 2 pi. Now in this, what is a variable? We discussed that with the time, if because I'm differentiating with the time the y is a variable because y just keeps on changing. W is the width of that coil, it will remain constant. So when I differentiate this, I'll get it as y divided by y plus w, and then differentiating the numerator and the denominator part. So I'll be getting it as this will be 0 plus w times y, so y times w, then minus I'll be having y plus w. Okay, am I right? uh, Differentiation of this would give me 1 plus, sorry, it will be 1 into y, because differentiation of numerator would give me 1 and denominator would be as it is y, and the differentiation of denominator would give me 1, that into y plus w divided by y square. This is what I'm going to get after differentiation. So now my equation has become E is equals to, what can be cancelled here? One y can get cancelled. When I open the bracket, y gets cancelled. What remains is minus w. To remove that minus sign, if you wish, I can just keep that minus outside. As I told you, I am only interested in magnitude. So even if an answer comes negative, I will not consider that. So anyway, negative is coming. So to cancel that, I'm going to keep this minus sign outside. Okay, fine. So what will I get? Minus minus gone. Mu naught I L y minus w, so that w came, minus of the w got cancelled, divided by 2 pi. What I get here is y into y plus w. This is what my EMF is. Now, as per the question, this y is equal to h at that moment we want. So just substitute that as here. So you'll be getting finally the EMF is equation as E is equals to mu naught I L W divided by 2 pi h plus, h into h plus w. So this becomes your EMF induced. So remember that this EMF induced we have found by using the Faraday's law. And as per the question, if I remember, they are not interested in finding the EMF. They are interested in finding the current. Yes, they have given us the resistance and they are interested in you to find out the current. That current can be obtained by using that just one step, last step, that current I is equals to E by R. So just divide this thing by resistance R and you got the current. So current will come out to be mu naught I L W divided by 2 pi h plus W and an R. This becomes a current. So this is one way of finding the current induced in that circuit. Now, because we already found the current, shall I also find the direction of the current? To how to find out the direction, there's also an important part. Most of the time students are struggling in finding direction. Magnitude is still easy. So finding direction, what we can do is we have to use the concept of Lenz's law. According to Lenz, what he said is, if there is any change that is happening, then the induced EMF produced because of that change will always try to oppose that change. Induced current will always try to oppose that change. So what is the change in flux happening? Try to understand. Initially the coil was here, afterwards the coil will move that side because of the velocity. So the coil is going away from the wire. So what will happen to the flux? The flux will decrease. In the previous video we had actually discussed based on this, that when a coil moves away from the wire, the flux will be actually decreasing. So if the flux is decreasing, that is the cause for the EMF and the current to come. So as per Lenz, the EMF or the current induced should always try to oppose the cause. So what is the cause? The cause is decrease in the magnetic flux. The magnetic field was actually into the board like this, and that magnetic field or flux is actually decreasing. So to increase that flux, the current induced should also produce a magnetic field in that same direction. Try to understand, right? The magnetic field into the board was generated by the wire, this wire, right? But because the coil is moving away, the magnetic flux produced because of that magnetic field which is going into the board is actually decreasing. So that decrease is causing the change in flux. So now the induced current should do what? Induced current should oppose the change. So what is the change? The magnetic flux is decreasing. The inward magnetic flux is decreasing. So to increase that, the current induced by the magnetic by the EMF, the current produced because of induction, that will also try to produce a magnetic field inwards. So if the magnetic field has to go inward, how should the current be flowing? I am using right hand thumb rule, thumb pointing the direction of magnetic field, and my curling of finger understands or gives me the direction of current. So that means current should be flowing like this, then only it will be trying to oppose the cause. So now I also obtain the direction of my current in the circuit, which is clockwise. I hope all of you have understood this. Wait, video is not over. This is just the first part, first method. I can also find out the same EMF in a much easier way by using motional EMF, right? That's actually much easier. Motional EMF is actually the easy part. So if this is the wire with current I, infinite wire like this, and here I have this coil, okay, length of the coil you can see is L, breadth is W, resistance is R, all that thing is okay. Now when this coil is moving in that direction with velocity V, then what is the EMF produced in this and this region? The two vertical ends, this part and this part, that is the width W. At this width W part, how much is the EMF generated? So if you have studied the BLV, you know that motional EMF BLV is only applicable when the velocity and the length corresponding to that, they are actually perpendicular. In here, for these two positions, these two parts of that loop, the velocity and the vector L, that is the length of the wire, they both are actually parallel to each other, you can see, right? And because they are parallel, what about the EMF induced here? Answer is 0. What about EMF induced in these two sides? Are these two sides parallel to velocity or perpendicular? They are perpendicular. So we will be getting EMF across these two sides, but we will be getting no EMF at these two positions. So that is one very important concept you should understand. So now this loop will behave like an electricity loop with one battery here, and that battery only we have to identify the EMF of the battery. So first of all, we have to identify how the battery would look. Will the battery have plus side here and minus side here? Or will the battery have minus side here and plus side here? Where is the plus of the battery and where is the minus of the battery? To understand that, you have to go to the NCRT's concept where we learned the derivation of BLV. How did we get that BLV formula? If you remember, there are two ways of deriving. One was using the concept of Faraday's equation, another was using the concept of Lorentz force. So if you use Lorentz force, that is, what is Lorentz force? The formula is F is equals to Q into V cross B. This is the formula that we can use, magnetic force acting on the charges. So when this part of the coil, this side of the coil is moving in that direction, then all the charges inside the coil is also moving in that direction. So if you use Fleming left hand rule, then magnetic field is into the board. We saw that magnetic field is into the board, the velocity is in that direction upwards, so force exerted is in this direction, the thumb direction. That means all the positive charges of this rod will accumulate in this side, and all the negative charges will accumulate in this side. Same story happens here also, all the positive will accumulate here, all the negative would accumulate here. So that means this rod is now behaving like a battery in this way. Very important. And the other rod is also behaving like a battery in this way. So that means the plus on the left side and the minus on the right side. Same story here. So now they are connected in series. You know, there's a series connection. And in series connection, when batteries are connected as plus to plus, it is considered as an opposition case. The batteries are opposing each other. So if I call this as, let us say, E1 and this as E2, then we can say the net EMF, E net, is nothing but E1 minus E2. That is from current electricity. We should understand. Now to find E1 and E2, we can use the concept of BLV, that is motional EMF. E1 should be equals to B1 LV and E2 should be equals to B2 LV. Length is same for both part. Velocity also same. The only thing that is varying is here the magnetic field would be different. It is closer to the wire, so higher magnetic field. This is far away from the wire, so it will be having a smaller magnetic field. So that's why magnetic field only I changed. Remaining everything is same. So if I substitute that here, I can say it is B1 minus B2 times LV. Now what's the formula for magnetic field? Mu naught I by 2 pi. What's the distance from here to the wire? We're talking about the distance being h, the moment when the distance is h. So that value is h. For the other one, it will be mu naught I divided by 2 pi. What's the distance to that? H plus w. So I'm having h plus w and then LV. So when I solve this, I'll finally get the value of the electric field, as this will go LCM. If I take h, I'll be having h plus w minus h. So h gets cancelled, w would be there. So I'll get mu naught I L V W divided by 2 pi h into h plus w. Just check, are we getting the same answer as the previous EMF? See, EMF comes out to be same. If you want to find out the current, please repeat the same step. Just divide it by resistance. You'll be able to find out the current. Okay. So this is now the second method. Okay. We would like to discuss here one more method. And that is the last part of the question. Remember the last part of the question? They were asking you, can you get the same result? Can you derive the same result using E is equals to integral of, closed integral of V cross B dot dl. Very nice concept. Okay. Now this is actually the vector form of the same, what you can say, motional EMF. So let us apply that. So when I apply this, I think you will understand why I said that EMF was 0 for these two ends. You'll be able to understand from this equation. So when I use this, you can see that it is V cross B. First of all, let us understand the magnitude and the direction of V cross B. Let's focus on that. So V cross B, which direction is the velocity? Velocity is in this way. Which direction is magnetic field? Magnetic field is inwards. Okay, so velocity is in that direction, magnetic field is inwards. Cross product direction will be always done by right hand thumb rule. You have to curl the fingers in the direction of the cross product. Cross product is V cross B. So curl your finger from the direction of V to the direction of B. So I'm finding my thumb is pointing to the left side. That means the V cross B's direction is towards left side. Please remember it. This is a direction of V cross B. Okay. Now, dl, we are going to consider a vector L, dl, throughout the loop. So let us consider the direction of the vector dl in this way. I am considering like this. This is the dl vector direction everywhere. Dl vector direction. Okay. So it's a choice of yours. You can choose it accordingly. So I am choosing the dl vector in this way. So I am getting the direction of dl vector in the same direction as the v cross b. So what can I write here? Can I do it in this way, that integration can be done in four parts? Integration for this part, upper part of the loop, the left hand side of the loop, the lower part of the loop, and the right hand side of the loop. Like that, four parts of integration I can do. For the first part of integration, can I write like this? Integration of VB, V cross B. What is the direction of V and B to each other? There will be 90 degree. What's the angle? Because V is like that, magnetic field is inwards. So angle between them is actually 90 degree. So VB sine theta, that is sine 90, would be anyway 1 into DL, right? What is the angle between the V cross B and the DL? V cross B's direction is in this way and DL vector is also in this way. So angle between them would be 0. So for the dot product, one cos also should come. That will be cos 0. Like that I'll write cos of 0. Okay, so cos 0 is anyway 1. So I'll be getting V and B being a constant for everywhere on that wire. Velocity is anyway constant. Magnetic field is actually varying, but magnetic field is varying with the distance. So can I say every point on this wire will be having same magnetic field? So that's why that magnetic field would be also constant. I can take it out. Integration of dl I'll be getting for this part. Now what about this part? You see, very easy. The dl vector is downwards like this, whereas the v cross b would be again in this way. The angle between them is 90. So when you do the dot product, the answer will come out to be 0, because v cross b and dl, they make an angle of 90 degree to each other. V cross B and DL. Same story goes for this side also then. This DL is upwards and V cross B is in this way. So again, there also the answer should be 0. So now only integration has to be done for this part. So plus additional integration of VB DL. All logics are same. But now you check, what is the direction of the DL vector and V cross B vector? They're opposite to each other. So angle would become now 180, cos of 180 degree. Okay. Now, so if you integrate that, you'll be getting VB integration of DL cos 180 means negative sign. That's it. So now you can understand from here that if I take it out, I'll be getting VB. Okay. Then integration of DL. Just one moment before that, what is the value of this B for both of them? Will it be same? For both of them, the value of B will not be same, right? So for this one, I used to call it as B1 for the first wire. So I'll call this one as B1, and for that part, I'm calling it as B2. So this is B2 and this is B1. Okay, now integrate it. So in integrating DL, this part, I'll get the total length. What's the total length? They're calling it as L. So VB2L minus VB1, that is also L, that same length, L. Now just substitute the values of the magnetic field. So I'll be getting it as VL as it is. I'm getting it as B2 minus B1. I don't need to solve it further, but I can just show you here. See, isn't it the same thing that I'm getting? In that part, I didn't explain to you that why. I tried to explain to you that because of these being in the same direction of velocity, that's why I was not getting EMF. But obviously that was not a proper explanation. By using this vector now, you are able to understand, I believe, properly that why for these two sections there is no EMF and only for these two sections we calculate. You can see we are getting same answer. Yeah, here it is B1 minus B2, here it is B2 minus B1. But I told you, we don't care about that negative sign. Anyway, we are only interested in the magnitude. You will get the same magnitude. Once you get the magnitude, you can always find out the current magnitude also. Anyway, direction of the current can be pretty easily found out once you know that how the battery looks like. See, if you want to, here already we found the direction of the current by using Lenz's law. Here again, you can find out the direction of current. Which EMF is bigger? E1 is bigger or E2 is bigger? Obviously, see, E1 is the bigger one because I got finally answer positive. That means the subtraction is giving a positive value. So E1 is bigger. If E1 is bigger, then current will be decided according to the E1. So current will be flowing in this way. This is a current electricity concept. In series connection, whichever one is the bigger battery, that battery will decide the direction of current. So current will flow in this way. Same way here also, current should be flowing in this way. That black colored arrow is showing me the DL direction. Don't confuse. Okay, blue colored direction is showing me the current direction. I hope all of you have understood this. If you have any kind of queries, you please ask. Otherwise, we'll stop our video here. Okay, thank you very much.